Hi everyone, and welcome back to another AP Calculus video. Today we're going to talk about another method of integration called integration by partial fraction decomposition, or by just part. And so basically what it is it's just another way to do integration. So let's kind of walk through and review all the methods that we should have at our disposal at this point. So the first method that I always remind everybody to do is to check your formulas. So we've got a couple hidden things that always show up, like tan inverse, sine inverse, things like that, natural log. Check your formulas and make sure that it's not something that you can easily do using one of your formulas. The next method that we always try next is always u sub. So can you do a u substitution with the integral that you're given? If u substitution doesn't work, and remember, u substitution can come in all sorts of forms. You can have two things that are multiplied that you can use u substitution on. You can have division that you can use u substitution on. U substitution comes in a lot of different ways. And remember, you're undoing the chain rule essentially. The next method that I always tell people to try is integration by parts. Now this is a BC topic along with partial fraction. And what integration by parts does is it says, okay, can we break it apart by doing two things that are multiplied together? So when we're multiplying, we have a product. Integration by parts is a really good tool for us. Now be careful, because some products look like quotients. So for example, when you have natural log over x or something like that, that is going to be something you'd want to use. Potentially integration by parts, or maybe u sub, depending on the nature of the function. But you want to be careful and understand that even though it's written as a quotient or division, you'll break it apart product. So these three methods you should try first. When they don't work, then what we want to do is we want to say, does it look like something I can use partial fraction decomposition? And what does that mean? And what does that look like? Well, essentially, suppose we have a function that looks like this. 5x minus 3 over x squared minus 2x minus 3. We have a function that looks like this. It's called a rational function, and we have a situation here where we can decompose this into two functions that got added together. And the reason I know I can do this is because I'm going to remember that when I have something like a over x plus something, or b over x minus something, and if I want to add those together, suppose, and it may or may not look like this, but if I want to add those together, there's a way to get a common denominator and combine like terms and turn two fractions. Well, partial fraction decomposition basically is undoing that work. So if I back up a little bit and take two functions that I know, so for example, if I take the functions 5 over 2x minus 1 minus 2 over x minus 3. Remember, this subtraction, I can write it as plus a negative. And if I wanted to combine them together and simplify this expression, I would have to get a common denominator. So what I would do is I'd multiply by what's missing. So here on the on the left, on this first fraction, I would multiply by x minus 3 to get a common denominator of 2x minus 1 times x minus 3. Over here on the other fraction, I would multiply by 2x minus 1 over 2x minus 1. Remember, you have to do the same thing in the numerator and the denominator so that you're multiplying by 1. Now, when I do this, I end up with a situation that looks like this. 5 times x minus 3 minus 2 times 2x minus 1, all over that common denominator of 2x minus 1 times x minus 3. And when I put it all together, I get 5x minus 15 minus 4x plus 2 over that common denominator. And when I combine all those like terms up, let's see, I get 5x minus 4x, that's going to be x, minus 13, all over 2x minus 1, 3. So the idea here being that I can combine things up, I can combine my like terms, I can get one big fraction that came from one smaller fraction, or that came from adding two smaller fractions. So this denominator could be multiplied out. perhaps we distributed and we got something that looked like this. X minus 13 all over 2x squared. It'll be minus 6x minus 1x, that's minus 7x plus 3. So the idea is we're starting here, and our goal with partial fraction decomposition is to get back to where we came from and to undo all this work that we saw play out. So let's kind of review, now that we've reviewed how to get to the starting spot, let's talk about how we're going to. Let's start with a problem like this. Now remember, we want to make sure that we always walk through our check. Number 1, is it a common integral? No. Number 2, can I do a u sub? Now remember, just because it looks like this doesn't always mean that it's going to be a partial fraction decomposition. So to test for u sub, I would want to do this. I'd say let u be the denominator. And then what would du look like? 2x minus 2 dx. Well, if that's my du, I would want my du to look like what's left over after I denominator as my u. So here, 5x minus 3, there's no way that I can make this look like 5x minus 3. I would have to factor out some sort of constant here on the right-hand side, and the only thing I can factor out here is a 2. There's no way I can make it look like 5x. If there is a way, by multiplying or dividing by a constant, to make that du expression resemble that 5x minus 3, then I know it's a u sub problem. Here, I know u sub won't work. So I know it's not a common integral. I know I can't do u sub. Integration by parts, I don't know that that's an option here, because we would have 5x minus 3 times 1 over x squared x minus 3. And as I think about what would happen with du and u and dv and v, I don't want to go there. So the next thing I'm going to try is the denominator factorable? So I'm going to see if I can factor the denominator, then I can do a partial fraction decomposition. So I'm going to look here and see, okay, this factors into x times x, and sure enough, minus 3, 1. So check, the denominator factors. I'm going to do a partial. So here's how it works. I'm going to go under the assumption that this 5x minus 3 over x minus 3 times x plus 1 came from something over x minus 3 plus something else over x plus 1. I'm going to assume that the two factors started out as individual little fractions. Then what I'm going to do is I'm going to go through the process of getting a common denominator. So my common denominator is x minus 3x plus 1, so I'm going to multiply here by x plus 1, and I'm going to do the same thing here in the denominator, x plus 1. I'm going to go over to the other fraction, and I'm going to multiply by x minus 3. I'm multiplying by what's missing to create my common denominator. So then my next step is to do this. Write it out as a x plus 1 plus b times x minus 3. And it's all over that common denominator of x minus 3, 1. Now, let's take what we know about having two equivalent expressions. If I already know that the denominators are the same, then that means that the numerators must also be the same. So what I'm going to do is I'm going to ignore the denominator, and my goal is to solve for a and b. So to solve for a and b here, I'm going to set up an equation that looks like this. The numerator of the left equals the numerator of the right. Now, to solve for a and b, there's just a real quick, easy way to do this. And that's by creating and forcing values to be. So I'm going to start with the 0 for the b, x minus 3. And I'm going to let x equal 3. The reason I'm going to let x equals 3 is because 3 minus 3 makes 0. I'm going to force this to become a 0. That cancels and wipes away the b. When x equals 3, then I have a times 3 plus 1 equals 5 times 3 minus 3. I can solve for a. So I get 4a over here. I get 12. That means a must be 3. Then I'm going to go and I'm going to force the a term to be 0. So I'm going to say let a, or let x equal -1. When x is -1, then I get this situation. 5 times -1 minus 3 equals, this will become 0, so the a term goes away. So all I'm left with is b times -1 minus 3. So this becomes -8 equals -4b, and I can solve for b too. So now that I have b, and now that I have a, I'm going to go back up and I'm going to show you why this partial fraction decomposition is so valuable. If I zoom out a little bit here, I'm going to remember that I started with a over x minus 3, b over x. A over x minus 3 plus b over x. Well, now that I know what a and b are, I'm going to put those values in to that equation. 3 over x minus 3 plus 2 over x minus 1. Now what I've done is I've created an equivalent situation. This is equal to that 5x minus 3 over minus 3. Remembered and copied it, right? Yep. So I've created an equivalent situation. And remember, if my goal is to integrate this side, if these are equivalent, I can just easily integrate this. And by creating my partial fraction decomposition here, I've made it so that I can integrate these two smaller fractions. Because we should be comfortable now knowing that we can do term-by-term integration. And then when we have x minus 3 and x minus 1 in the bottom, since these are linear terms, I can anti-differentiate them and integrate them and find their antiderivative as the natural log of x minus 3, absolute value of, plus 2 times the natural log of x minus 1. C. So the solution to this differential equation can be found by breaking it apart into two smaller fractions for whom the antiderivative is just log. So this is why the process of partial fraction decomposition is valuable, because it allows us to break it down into something easier to integrate. Let's see another one. We'll start with this one here. Now remember, can we do a u sub? Is it a normal one that's on our formula sheet? Is it an easy thing to integrate? Is it integration by parts? And here, if u sub was used, u would be 2x squared minus 7x. du would be 4x minus 7. There's nothing I can factor out to make it equivalent to x minus 13. So since it doesn't line up, I can't do u sub. So then I'm going to factor this denominator. 2x and x. Let's see, can we play around with it? How about minus 3 minus 1? Always check your factoring. Make sure that when you remultiply it out, it always recreates. And generally, you only have to check the outer and the inner function when you're factoring a trinomial like this. You get minus 6x minus 1x. Always check your factoring. So now I'm going to set up my partial fraction decomposition. 2x minus 1 times x minus 3 is equivalent to a over 2x minus 1 plus some b over x minus 3. My next job is to get my common denominator. So I'm going to multiply here by x minus 3, 2x minus 1, 2x minus 1. And then I'm going to skip right to the part where I take the numerators and set them equal to each other, because I know I'm going to have the same. So I'll have a times x minus 3 plus b times 2x minus 1. And now I'm going to force some zeros. I'm going to let x equal 3. That gives me 3 minus 13 equals, the a term goes to 0. The b term goes to 5b. So negative 10 equals 5b, negative 2. I have b. Now I need to find a. So for a, I'm going to let x equal 1/2. So that's going to turn this into a 0, right? Because the whole goal is what is going to make a 0 here for the b, what's going to make a 0 for the a. When I do that, I get 1/2 minus 13 equals a times 1/2, 3. Well, I'm going to think this one through. I'm going to get negative 12.5 equals negative 2.5a. And when I do my division there, I think 5. So then we set our functions up. We've got a is 5, and we set up our integrals. And here we have 2 integrals that are going to end up involving natural log. But we want to be really careful because there's going to be some u sub in here with the 2x minus 1. It's not quite right. And then also we're going to have subtraction. So one trick that I do is if I have a negative, I just make it into subtraction. So remember, we're integrating each piece separately. So this becomes 5 times the natural log of 2x minus 1, but I'm going to divide by 2. If we do a u sub with that one and let u equal 2x minus 1, our du equals 2 dx. So we end up having a 1/2 du put in. So we're going to be dividing by 2 ultimately. And if you don't believe me, you can kind of work it out. At this point, that's something that I would hope that we're comfortable seeing play out. So then we go minus 2 times the natural log of x 3. Now, in general, we can kind of leave this as it is. But one thing I want to make sure that you understand is that on a multiple choice test, you would not see this answer the way that it's written. In fact, you would see it condensed and using the properties of logarithms to condense. So we might see it written like this: 5/2 times the natural log of 2x minus 1 minus 2 ln x minus 3. Oftentimes we can take and condense these natural logs and kind of make them into one. Now this one's not as easy to do. You would have to take and remember that these can be powers. You'd have the natural log of 2x minus 1 to the 5/2 power. You could turn this into something squared. When we do that, we can actually drop the absolute value bars because when we square it, it remains positive. And then you could rewrite it as a quotient. Now, this is kind of an ugly quotient, but it would end up looking like this: 2x minus 1 to the 5 divided by x minus 3 squared. So this is kind of a little more complex than maybe what we'd want to do this with. You could definitely stop up here at this first line as a solution. But I just want to reiterate, those natural log and those logarithm properties will come into play when you're evaluating logarithms. You will need to understand how to go from subtraction of 2 logs to condensing it to 1 logarithm. So let's keep going. Let's try another one and make sure that we're enjoying, applying these partial fractions. Now, remember, I always say check, check, check. All the methods, make sure that you go through the list. So is it a common function? No. Can I do u sub? Well, if I let u be the bottom, we like to let u be the denominator, then du equals 2x minus 4. Now remember, my goal is to make it look like x plus 2. So can I factor anything out? Well, I can kind of factor a 2 out, but I'm left with x minus 2. So nope, it's not going to work. So then my next step is to factor. So I'm going to go ahead and factor this into x plus 2 over, we're going to say probably minus 5 plus 1. Don't ever say 2 things are equal unless they actually are. So make sure to include the integral. But I factored the denominator. Now I'm going to set it up for partial fraction position. And if at any point you want to pause the video and see if you can make it play out and work out, I would encourage you to do that and then check it. I'm going to keep going for those who want to kind of follow along. So here we go. We're going to have x plus 2 then we get our common denominator, x plus 1. Sometimes you'll get so good at this that you can kind of jump to x plus 2 equals a times x plus 1. You can just jump straight to this, but be really careful. Make sure you're writing out those steps where you put a over a factor, so that when you put a and b back in, you're putting them in over the correct subtract. Don't mix them up. So now we're going to let x equal -1. So that's going to give me -1 plus 2. That's going to give me 1 equals b times -6. So -1/6 equals b. And we're going to do the same thing over here. We're going to let x equal 5. So that gives me 7 on the left equals 5. That's 6a. So 7 over 6 equals a. So now when we plug in our a, make sure you put a and b over the right values. Now we're ready to go ahead and integrate. 7/6 times the natural log of the absolute value of x minus 5 plus -1/6 times the natural log of. Now we could also change this to fraction. So here's my partial fraction decomposition. This is how we can use it to integral. Now, one side note, if I had gone up here, and here's where our critical thinking comes in. Suppose I change this problem, and suppose I make this a plus. If I change that one aspect of this problem, the factoring becomes different, but also, more importantly, it becomes a u substitution problem. Because the minute we have x plus 2, case, x plus 2 over x squared plus 4x, we're trying to integrate that, and our u becomes 2x 4. Or our du becomes 2x plus 4 because we let u be that denominator. Now, we can factor out a 2 and get x plus 2, meaning that we're going to have 1/2 du equals x plus 2x. So all of a sudden, there's my 1/2 du. This becomes a different problem. I would have my 1/2 here, du, and my answer would be 1/2 times the natural log of that denominator, x squared plus 5, plus c, of course, just by changing one simple subtraction to addition. So be careful and mindful about that u sub. It's not always going to be partial fraction decomposition. Sometimes it's going to be a u sub problem. That'll be the thing. Now, partial fraction decomposition probably would have worked just fine, but it would have taken a little bit longer. So be mindful of the different techniques that we have at our disposal. Now we're going to take a look at an example where we have to do a little bit more work before we can use partial fraction. When I look at this, I know that if I try to let u be the denominator, u substitution is going to fail. du is. I know that I can't do anything with it in terms of trying to make it fit with integration by parts, or it's just not going to work. So what I can do is I can simplify this. And I notice that the numerator has a bigger exponent. Say the degree of the numerator is greater than the I have x to the 4th and x. So this tells me that it's a candidate for polynomial. Now, polynomial division is not something that a lot on the AP, but it's something we want to be prepared for, and it's going to set apart those 4s and 5s. That's kind of a skill that knowing how to do that could earn you extra. So let's take a look at how polynomial division will work. So what I do is I set it up like this, and I take the x squared, and I'm going to put a placeholder. For every x that I'm missing, I'm going to put a 0x. And then inside, the outside is called the divisor, the inside is called the dividend. And so this is where we put 3x to the 4th. And again, I'm going to use some place. 0x cubed, 0x squared, plus 0x, 1. Now, what I'm going to do is I'm going to start by looking at the first term. And I'm going to say, what would I multiply x squared by to get to 3x to the 4th? Now, if these were numbers, I'd say, how many times does x squared into? With polynomials, it's easier to ask the question, what would I multiply? You essentially get the same result, and it's easier to comprehend with polynomials. So what would I multiply here by? 3x squared. So the reason why it's so important to put these 0 placeholders is because it helps us line up our values as we're trying to find the result. So then what I do is I take this 3x squared, and I multiply it by each of the terms in that side divisor. And when I do that and put them under here, I'm going to line them all up. So I get 3x to the 4th. I want these to be the same, plus 0x cubed minus 3. Then what I'm going to do is I'm going to subtract that result from the 3 terms above. So the first terms cancel, then I get 0, and then 0 minus a negative turns to a plus 3x squared. Then what I'm going to do is I'm going to bring down the 0x, and I'm also going to bring down the 1, because I know that I'm going to need to bring it eventually. And with the 0x's happening, I just know that I'm going to have to. Now, if you don't know that you need to bring 2 terms down at a time, it'll become obvious. So then what I do is I look at this 3x squared and I say, what do I multiply this x squared by again? Always looking at that outside term, that first term. What do I multiply with that to make 3x squared? Well, the answer is easy. It's 3. And I'm going to line it up over here above my constant. So I'm going to have a 0 here. So then I'm going to do some multiplication again. So 3 times 3x squared is 3 times x squared is 3x squared. 3 times 0 is 0. And then 3 times negative 1 is negative 3. I'm going to do my subtraction. I'm going to get 1 minus negative 3 is 4. This is my remainder. And I know it's my remainder, and I know that I am done because there's nothing I can multiply x squared by. So now what I'm going to do is I'm going to rewrite this using the top and the 4 as my remainder. And it's going to look like this. I'm going to have the integral of 3x squared plus 3, so that's from the top, that's my quotient, plus the remainder, 4 over x squared 1. This is what I'm going to integrate. And now it becomes a little easier to do, okay? Because now I know that when I integrate term by term, this just becomes x cubed, this becomes 3x. And then when I integrate this guy, this is where I'm going to use that partial fraction decomposition. So I'm going to go ahead and factor that denominator and start using my partial fraction. So I know I'm going to have a over x plus 1 plus b over x minus 1 is going to equal 4 over minus 1. So now multiplying by what we're missing, x minus 1 plus 1. Now I'm going to jump straight to a times x minus 1 plus b times x plus 1 equals 4. I'm going to let x equal 1. Then I get 2b equals 4. So b must be 2. And then I'm going to let x equal negative 1. And that's going to cancel away the b. And I get negative 2a. A must be negative 2. So now I can go back over here and start setting up my integral. So I'm going to have negative 2 over x plus 1 plus 2 over x minus 1. And that's what I'm going to integrate. So I'm going to get negative 2 natural log of x 1 plus 2 natural log of x minus 1. But of course, I can't forget to tack that on to what I got earlier. So there were a couple other terms up here that I integrated. So this replaces this. So now my final answer is this: x cubed plus 3x minus 2 ln x plus 1 plus 2 ln x minus 1 plus c. And of course, there are some things that I could do with this in terms of combining my natural logs, but I'm just gonna leave it like that and call it a winner, because sometimes that's just what you gotta do. So sometimes when we do these big problems, it can seem like a lot of work, but we just have to power our way through. Know that we have the tools to be able to solve all these problems. It's just deciding when and how to use it. And that comes with experience and practice. So keep trying, keep practicing. You're gonna get it. You've got this.